All right, had some issues with the recording. Now we're good here. So we're starting integral calculus here. I'm going to catch up where we are. And 5.1 is all about areas. That is integral calculus. And from geometry, we know that so this is just catching up here. I know we're kind of like on. So from geometry, if we think back, we have certain areas we know of things. We have certain formulas for it. So rectangle, triangle, square, parallelogram. Let's see, a rhombus, a kite, diamond. I think those are all the different types, depending on what shape it's in. Trapezoids, circles, and any kind of polygons. But calculus takes it to a different level where I can get an area of whatever I want. That's what calculus does. And they do it by using something called integrals. All right. But before we get there, we got to go to this guy. And so this guy says, what is the sum of the expanded form of this? And so this is Greek notation. This is a capital S. It just means sum. This guy's called the index. This is where we begin. 1 is where we begin, and we end at 6. So, and this is the formula. So if we say I is equal to 1, 1 goes in here. Once that is done, we go back and we say, okay, what else can we plug in? We can plug in the 2, and it always goes up from our initial index. And we go to here, we all the way up until we get to the last. Then we stop, and then we just add them up. And the answer is 21. Cool. The only difference is, for this one is, now we go from 1 to 3, and we got ourselves an x squared. Anybody got an answer yet?
14.
14 is good. So it's a 1 squared, because that gets plugged in, plus a 2 now being squared, and then a 3 now being squared. And then how about a 1 plus, what is it? 3 plus 9 or something. 4 plus 9, yep. Done. Next one on the list. So this one, you may have to use a calculator to solve. That one, you can't even get a calculator, so you have to sort of stop there. But try this one real quickly here. Nope. And the answers, let's see what you guys get or got. Let's see, 4 to the 5th power, is that right? So 4 to the 5th power is 1,024. Then you get the next one, which is 4 to the 6th power, would be 4,096. And then the grand total, 5,120. All right, when you include variables, it gets even worse because at this point, not worse, but at this point you can't add them together, right? They're not just numbers anymore. So x to the 2nd power times k would be x to the 4th. And then next one would be x to the 6th because you're multiplying 2 each time, is that right? So I got 2, I got a 3 in there. 4 times 2 would make an 8. I think that's where I stop, is that right? It goes only from 2 to 8. At this point, you can't simplify it. You just leave it just like that. Cool. And one more. So now notice this one, interestingly enough, it does not stop. It goes I starts at 3 and then goes up to n, whatever n is.
What's crazy to me is we learning things that would back in the day took hundreds, if not thousands of years. And you require a PhD in order to find out. And we're doing this in what? Just a few months.
What did I just say?
I think it comes out
5, 6, and 6, 7.
no, it's 3 quarters and 4 fifths and 5 sixths. You're summing it all. Yeah, it already goes over the all. Because
So it's kind of like a limit.
it goes closer to closer to 1.
That's what I just said.
Yeah, but it's over 1. Like you're adding together.
Yes, you're adding all the bugs together. So yeah.
Oh, I
But
see
not
what-
individual, but you're summing. Yeah. Mm-hmm.
So
But yes, the
one's
numbers
one
get closer
to 1, but they're all going together.
Wait, so that's infinity?
So you could write it as 3/4 plus 4 fifths plus 5 6 plus 6 sevenths. You could write the 1 in the back of it as well. That's fine. As long as you go ... plus n over n plus 1, right? Because you're going to go to n, whatever n is, you just kind of specify, okay, that's at least what I got.
And then use it like that.
You can leave it just like that, yeah. So you have to provide the formula all the way at the end, which is what we're going to be doing when we're going to be doing ours. Okay, we're good there. Let's go backwards. So can you guys give me the formula if I give you this iteration?
F for A should be epsilon I equals 1. 12 is the top.
Sounds good.
What does it say like the word in the sentence?
Oh yeah, write the. See, can I move this? Write the sum. And sigma notation.
Sum and sigma.
Write the sum and sigma.
I'm getting there. Sigma notation.
So let's go. It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that means I'm going to make my little sigma notation there. Looks like I is equal to 1, which I'm starting with. Looks like I'm going up to 12, and the formula is just I itself. Are we good? Easy enough. Do we always use I? No. Sometimes they use J. Sometimes they'll use K. There's rarely, but they'll just use N as the number. So N is equal to, because N is usually a listing number. But I, J, K usually are the
Elements.
that we use. Okay, next one. And we got the next one now.
Sigma I equals 1, 12, and 1 over I squared.
Perfect. Yeah, 1 over I squared. Looks like it starts at 1, and it keeps on going. So it's up to 12, and then each time you square the number itself. So in the first one, the 1 squared just became 1, so you got simplified out. And that's just sometimes you have to be careful for in the homework. Okay, this is simplified out, but what would be if it was not simplified? Then you're like, oh, now I see the pattern. Okay, and then, of course, let's introduce subtraction and addition. All right, and the question is, does it always start with 1? We like to start it with 1. It doesn't necessarily have to start at 1. Most of the time it does. The next favorite number is 0. It may start at 0, and then it does it. So let's go with C. And you kind of see what the formula is going to be.
No, and then you give us the formula too. At the end.
Yeah. So anything that goes up to N, that's kind of nice because it actually just gave us the formula. Now, the only other thing is, how do you get a 1 out of a situation with exponents? It's 0. So starting point would be 0. The natural starting point is 0. And then how do we get the little switch between the negatives and the positives?
You got a negative 1.
Yeah, get a negative 1 to a certain power. That's perfect.
It would be the I power instead of the N power. It would be negative 1 I.
Thank you so much. Yep. Is this pen working here? Let's see. Yep. This would be I power. This would be I power. All right. The other thing is this. What happens, and what if I really, really, really wanted to start this at I equals 1? How do I?
1 I minus 1 I minus 1.
Okay, so I want to start this here. And then I'm going to still finish this off here. And so are we okay with I over here? We're just going to subtract 1 from it because that will give the iteration back to 0 if we start off with that. And so this one's the same thing here. This would be x to the I minus 1.
Go to the n minus 1.
I'm thinking I'm going to go to n plus 1. Is that right? So I'm going to go just a little bit ahead. So when I subtract 1, n is the last one that I do. Right? Okay, are we good with that? So real quick here, if I were to plug in, n plus 1, minus 1, it'll give me the n that I finished off with right there. So kind of just thinking, how do I get to the place that I want to get to?
When we do the dot 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 plus whatever, do you want us to simplify that notation or do you need it like exact plug it in and go like plug it in?
Say again.
So like if for the red one, if we plugged in, we did the dot dot dot, do you want us to do the full -1 to n plus 1 minus 1, or do you want us to do it like -1 n x n? Like, do you want us to simplify that?
Sorry, can you say one more time? Sorry, I didn't quite get it.
So, for like when we're writing this problem down, on the red one, do you want us to do for dot 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 parentheses -1 and then to the power of n plus 1 minus 1, or just simplify it to n because the ones cancel each other out?
Oh yeah, you don't
Want us to simplify with that file notation?
need to do this right here, right? The I minus 1, the n plus 1, you have to write it in here, right?
Mm-hmm.
When you write it in here, when you do the I minus 1, it does come back to n, right? I just showed it.
Right.
I don't know if that's what you're saying, but go ahead. Say it again one more time just to make sure. This guy, you're referring to this guy?
Just like write. Could you like just write the answer like for like if we did dot 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 for the red one, like how you would write that out?
Oh, gotcha.
The final value.
If I were to go back, because this is the final value here, right?
Yeah.
If you were to write it out, though?
Yes, if you were to write
Oh,
out
yeah.
like the n and for the I.
Oh, sure, gotcha. It'd just be n, yeah.
You can't simplify. Okay.
Yeah. Okay. You'd cancel it and just give you
I
at
don't know if
least...
you want us to have that final n value, like n plus 1 in that file.
No. Thank you for clarifying. Okay, and let's GM. Let's do some special cases now. So what happens if?
Special cases.
What happens if?
Very scared.
Special cases, or you can say specific formulas, because that's what we'll need. So the question is this: if I am adding the same, or 1 actually, technically, 1 over and over and over again, until I get all the way up to n.
So infinity.
N being, yeah, whatever number, right? And this guy here. Oh, perfect, okay. So if I go from I is equal to 1 to n, but if it's of 1, just 1 by itself, so that means I have 1 plus 1, right? My index count goes from 1 all the way to n. Notice that's why I like starting with 1. How many 1s do I have? N number of 1s. Can I shorten this formula down? So I say...
Enough.
Just n itself, okay?
Sorry.
So bracket that if you need to. So if your I is equal to 1, and you're summing 1s from 1 to n, it's just n.
Is that constant?
Sure, yeah, as long as it's 1, and as long as you started at 1. But now let's go with the constant now. So what happens if it's not 1? What happens if it's a 2 or a 7 or a 12? What happens there?
So why does it equal n? Is n also just infinity?
No, because we're not going to infinity. We're starting at 1. We're going to finite number of terms, but to n. But n is not specified.
So,
Right? N could be 12. N could be 24. N could be 648.
and the answer is just straight n because
We're just adding the same number of those values of 1.
it's 1.
Because it's 1. So now let's see what happens if it's another number other than 1. You don't have to do it again. I just have it on each slide here.
Then it'd be 2n.
Mm-hmm. Perfect. Yep. So C stands for 2 and 12, 24, whatever. We'll get to exponents in just a bit here with I. So, yeah. Okay, so same thing happens here. It's just going to, instead of 1, it's going to be a C plus C plus C plus C. How many number of times? And number of times. And if that's the case, what's the addition of these guys? CN, yep. CN or NC doesn't really matter here. I got myself NC or CN, it wouldn't really matter. All right, and then the tricky stuff begins. But again, we're just trying to get a formula out of it. All right, we good so far? Cool. Bracket it off if you like, or box it if you like, whatever you like here. Let's go now to an I. So how about this? Special case, special formulas? I got this guy now. Oh, let the fun begin.
I equals.
So let's see what happens
so
here.
is it like the 2 and 1/2 in
Okay.
n plus n over n I over 2.
Okay, let's begin here. Let's see. This really is a fun one here. The way we develop it here. So let's see what we have. We have is this. So we have 1 plus 2 plus 3 plus 4, right? So on, so forth, all the way to get to n. So n minus 1 in parentheses and n. So that would be like the n right there.
Oh, you split it in half, right? And then you combine. It's 1 times 50.
Okay.
Something like that.
Perfect. Yeah, you guys have seen the formula. And did we talk about how? Let's see.
I said add every number between 1 and 100. So everything adds up to 101.
Perfect. Yeah. So in 5th grade, Frederick Gauss told him to add from 1 to 100.
He made the Gauss.
Let's go into it because we got to go into it. So in those days, they did chalkboards, right? If you wanted to add from 1 to 100, it was total busy work because what you had to do is you had to go like this. This is, mind you, this is like 3rd, 4th graders, or 5th graders, right? So you go like this. You write it 2, and you put a 2 here, right? Oh, sorry, not 1 plus 1. Sorry, not 1. 1 plus 2 is 3, right? We put a 3 here.
I remember those.
And then we would erase this piece. And then we would write, okay, whoa. Not write that here. Let's see. So we have now ourselves this right here, right? So then we go 3 plus 3 is 6, right?
Wouldn't it be 4? No,
1
you're
plus
right,
2.
it's 3.
Yeah, okay. Make it sure. And then all of a sudden, like, whoa, hold on. That's going to be, so I erase this with my eraser, put a 6 now in there, right? But then I have to keep track of what number, what iteration I'm on as well, right? So then I got to keep now track of this guy here, right? So I just did 3. My next one is 4. So then, oh boy. So I go like this. I got 6 in there now. And now I got myself, make sure I have an iteration of 4. So 6 plus 4 is 10. I erased the 6. I put down a 10, right? And then I know that I'm now iteration of 5. Is this tedious? Could you imagine how long it's going to take 5th graders to do this here?
And then you got this 5th grader's like, hey, wait a minute.
So suppose the story goes, the teacher goes back to his desk. And within about
What did he do?
4 minutes. Frederick Gauss comes up and says, "Oh, I got the answer." And the teacher's like, "What? 4 minutes? What? So are you messing with me?"
Fast.
Yeah.
He must have used
ChatGPT.
artificial chalk.
I'm at 6 now. Oh man, this is tedious. Frustrate me here.
So either the teacher didn't want to teach the class that day, or he
One of the torture.
everyone annoyed him.
Is this the one shows over mad at us? He's gonna
Yeah,
Add
we
from
know
1
how
to
to
100.
do it, so because again, 4 minutes.
No, 1 minute. No, he had to figure out the formula. That was the
He
formula.
doesn't know
Uh-huh.
that
We
he's
know
41
the
now,
formula.
so if it's over mad at
Yeah,
us.
let's go with it
He
here.
knows the formula.
So what Frederick Gauss did is this. He actually thought of
Oh, thanks, Weston. I wish I thought of that.
let's see, let me erase it here. Make the board bigger, and then we'll do our problem. So you don't have to do our problem yet. So he said, okay, that's the case. I'm going to make x to be 1 plus 2 plus 3 plus 4 all the way up to 99 plus 100. We good? And if I make a second one, x is equal to, and I just reverse them backwards. So this is 100 plus 99 plus 98, right? And I'm going to do the same thing. I'm going to go over here. This will be plus 2 plus 1. Very good there. And here's a fun thing that happens.
Everything.
This is 2x. This is going to be 101 plus 101. And then, that is so awesome. Could you see the excitement of a fifth grader? Saying that, I think I've just discovered something new, teach. How many of these guys do I have? I have 100 of them now, right? So then, right, because there's 100 of them, right? Because we have iteration, there's 1.
Right.
There's the second one, right? So he says, okay, that's just multiplication. This is 101 times 100. So in order to solve for x, which is the 1, right, the initial one, all I got to do is divide by 2, and I got myself a formula. It is 100, right, times 101 divided by 2. That's my formula. Love it. Comes up to the teacher. And teacher's not too, apparently the way it goes, the teacher was not too excited about him figuring that one out. So let's go with ours now. So if I reverse this, if I say the exact same thing here too, I say, okay, I'm going to write the exact same formula here. Mine's going to start with n, then n minus 1, and I'm going to go all the way down to 4 plus 3 plus 2 plus 1. And just like Frederick Gauss, I'm going to add them up. What do I have?
N times N plus I over all of 2.
Yeah, I have 2 of these formulas, right? And notice what happens here is I add down. So 1 plus n. That should just be n plus 1. Are we good there? What is 2 plus n minus 1? Another n plus 1. Perfect. And I'm going to have the same thing here, right? I'm going to keep on going. And how many of these do I have? N of these guys. So now can I get we call it an explicit formula. Can I get an explicit formula for this? Yeah, it's going to be n plus 1 times n. True? We're just multiplying now. All right, let's write it down first here. Go. Okay, we good there with that? So the explicit formula would then be summation from 1 to n of I is equal to n times n plus 1. And then divide by 2 from both sides, because we technically just have an equation. And now we can bracket this here. There's our next one. So we got 1, 2, 3. So far we have 3 different equations, right?
Special cases?
The special cases, yeah. So the other two, they're pretty hard to do, pretty long to do. So I'm going to give them to you. We'll just need these. So if you have a desire at the end of the year to say, hey, Mr. D, I want to present on something, if you want to do the proof for the following, that'd be cool too.
Talk about special.
All right, so we have 1, we have a constant, we have I. So let's go I to the second power. Sorry, what do you need that?
Different boxes. These are my favorite special cases.
This is I to the second power. Notice it's a little bit longer. I'm going to go I to the third power. This one's interesting because this one's actually shorter. It's the square. That's kind of weird how that worked out, or very unusual how that worked out. It's actually, so I to the third is a explicit formula is a square of the I formula.
Roger,
Yeah.
on a test, will we have a formula sheet of all the summation laws? So
Yeah, these ones right here, yeah. Uh-huh.
can you break summation through or like distribute it through addition?
Absolutely, yeah. And I just kind of assume that makes sense to you guys here in the next one.
You
But,
assume poorly.
Okay, are we good there? Does this make a lot more sense than Monday's class? Except for Weston. That's... Okay, tell me, you guys ready to go on?
Yeah, the part of the rush was just the rectangles.
Yeah, that's the one to get confused. Yeah, sorry about that. Okay.
Which I swear I learned before, but I forgot.
All right, so let's figure out. Just check something out.
I did the fourth power just be squared.
I don't think so. No. Okay. All right, so let's jump with it here. So last part right here. So let's see. Let's go to a product. What do I want to do with this one here? Why did I have it only 6? Okay, change up things as you guys do
Why
this.
not I minus 2 instead of I minus 1?
I just want to change up a few things. Just real quick here, guys. I think this is the way I want to do it. I'm not sure why I had. I'm going to put a plus sign in here instead of minus. Good there. And I think let me bracket this off. I think I did A and an A prime. I want to do it 2 different ways. I want to show you the fact that it is. We're going to do it 2 different ways. Okay, first way is if you plug in 3 into here, right? This would be 3 and what? 3 times 5? True. Do you guys agree?
Yes. 15.
Okay, and then if I put a 4 in there, it's 4 times 6. Everybody there?
Mm-hmm.
And what, 5 times 7? And then anybody got an answer yet?
Times. Oh, it goes to 6.
And 6, right? That's right. It's a plus sign still, right? So 3, 4, 5. I still need the next one here. Erase. And 6 times 8. Anybody give me that answer right here? Quick calculator, if need be. This would be 15 plus 24 plus 35 plus 48, I believe.
15 plus 5 is 50.
112?
112. Anybody give me a second on the 112?
112. Or is it 102?
That's you?
Or is it 102?
122.
How did you just get 2?
132, 122, and 112 and 102. So if you want to give an answer here, because
So it's 2.
it's a 2 at the end.
I have 48.
Yeah, 132.
48 plus 16, 15, 24, 35, 48.
It's
122.
That's correct. It's 122.
So 35 plus 15 is 50.
Yeah.
24 plus 46, or 24 plus 48 equals 72. 72 plus 50 was 100. Yeah.
122?
That's what I
Perfect, okay.
Knew it.
Yep.
That's why you
Let's do this here. I want to know if I have to do it this way, or I can split it off with this little plus sign. So let's see if I do it this way. So if I were to distribute this little I over here, I is equal to 3, going to 6. Now I have myself I squared plus 2I. Everybody agreed there. And then I want to see if I can split this off across a plus sign. If I go to here, I squared. If I go to here, notice what I did is I just split off these guys. And I want to see if I get the same answer. Are we good? So.
Isn't it like the...
Oh, like the limits. Remember, limits can move in and out of addition, subtraction, even multiplication. I just want to see if I get the same answer here. So, can we, in this little big bracket right here, put in a 3 squared is 9, 16, is that right? Plus 25, plus 36, plus, what's going to be here? This is going to be 6, plus 8, plus 10, plus 12. Okay. Can you guys add those up?
122.
For sure.
Yeah.
Okay. So we can move the summation sign through subtraction, addition. We can actually even do it through multiplication if we need be. But for us, it's just the fact that we can move it through subtraction, addition. Okay, that's one piece I wanted to take care of. We're good? The second piece is now, let's do this here. Based upon the 1, 2, 3 things that we just did, can we simplify this guy out? So notice the 2 is actually multiplying the I. Good? What I want to do is I want to simplify this as much as I possibly can. So what I'm going to do is I'm going to move the 2 and I'm going to move it out in front. Are we good? So running out of room. Okay, so how about this here? I'm going to move the 2 out in front. I have this here, I is equal to 1 of n of just I. So now do we have an explicit formula for I? Have we seen that before? I think it is n times over 2. Perfect. And then that little 2 on the outside cancels with this 2 on the inside. I got myself n times n plus 1. Oh, we're good. We made an explicit formula. I don't know what the answer is, right? But I just went from sum notation to just an explicit formula. We're good? Okay, putting both of those things together. Last problem. This one right here. Can we do this one? So first things first is, can I distribute the summation formula through a minus? Absolutely. So I'm going to go here. I'm going to go to this. I'm going to go to this. The only other thing I want to do is in fact, you know what? Can I take out the 2? If I take out a 2, what will be left over? Oh yeah, that's right. 2n would be left over, yeah. But I'm thinking this way. You can either do it both ways, right? You can just say 2 times n, right? Because it's c times n. Or if you do just a little trick here, if you can take out a 2 out of this here, you're left with a 1 in here. We good? And then you can take out a 5 as well. So notice what happens is when you take out, here's my little formulas here. We're going to write them off to the side here. We're good there. This little formula from a few slides ago, if you're adding 1 each time, you're just going to have an n. We good? Or if you want to keep the 2 inside there, it would have just been 2 times n. Minus sign. And here's your little formula for I. It's n times n plus 1 over 2. Now the only thing is we got to do is we have to simplify it out. So let's see, 2n stays minus, the 5 goes in for the n, as well as the n times n. We good there? So this would be 5n times n, which is n squared. Tell me if you guys are okay with that one. I'm distributing. I'm kind of doing 2 steps at once here. Maybe I shouldn't here. 1 second. Let me go back to here.
What's crazy someone moved to the coldest place on earth and said, ah, yes, I'm rather fond of Siberia. And he stayed.
Okay.
Sorry. She's why.
What's funny to me is they say that in the middle of
Yeah, it's fair enough.
Are we okay with that so far? Let's see, I do need common denominators, and then I also need to split off this fraction. Tell me if this makes sense here. It's going to be a 4n over 2. Let's see. Does that make sense? You guys talk to me there. Does that make sense there? So I split off the 2 there so I can actually move the 4 and the 5n around. And what I got was, let's do the n squares first. And it's a negative 5n squared over 2. And now I got a 4n subtract 5n. Minus n. I can leave it like that, but usually we would write it as negative 5n squared minus n divided by 2. Are we good with that? Does everybody make sense there? All right, y'all, and that is the end. So you guys have enough information to do Appendix-E. We good? Then on Friday, we'll actually look at 5.1, kind of put it all together. If you want to bring questions, homework questions from 4.9 as well, right, at that time, 4.9, and Appendix-E homework questions, and then we'll see how far we get through into 5.1. And so let the fun begin. We do something called integral calculus. We'll see how all this fits together.